So hello everyone, I'm Flemming, I'm a PhD student at MIT, and today I want to talk a little bit about my work on MarkovBounds.jl, which is a Julia package for stochastic optimal control on the basis of SumOfSquares programming. So in particular, I want to talk about stochastic optimal control problems that are vaguely of this form here, where we are given some stochastic process x of t and are trying to identify a feedback controller that allows us to operate this process at minimal expected cost, for example, as quantified by some accumulating stage cost and some terminal cost if the control horizon is finite. And of course, this is super general and includes many important classes of problems as special case, for example, trajectory following problems, reachability type problems, or the opposite of that in obstacle avoidance. So, and because this is so relevant, there's many techniques out there to address these types of problems. Reinforcement learning is certainly very popular, multi-stage stochastic programming is widely used, and the stochastic maximum principle. But what all these techniques tend to have in common is that they are in one way or another heuristic. So they either introduce some sort of approximations that then call into question whether the solution obtained is actually accurate for the original problem, or they provide zero guarantees on the quality of the obtained controller. So what's behind MarkovBounds.jl is something to address this issue. So in particular, the goal is to compute informative lower bounds on the optimal value of these types of stochastic optimal control problems, alongside with information to construct heuristic controllers, so that then down the line we can actually certify that a certain controller is near optimal, or at least bound its degree of suboptimality. So in particular, I want to talk about the case of controlled jump diffusion processes, which are stochastic processes that are driven by some deterministic drift that can further exhibit these stochastic vibrations as forced by a Brownian motion, and can further show discrete jumps in the state as triggered by Poisson counters. Moreover, I will assume that we know something about the state space of the process, so we will assume to know that either the process lives anywhere in Rn, or maybe is confined to the non-negative orthant, or some integer lattice, or something of that sort. And I will critically assume that everything about the process is described in one way or another in terms of polynomials. So in particular, for all the functions that characterize the dynamics of the process will be assumed to be polynomials both jointly in the state and the control action, and also the state space and the set of admissible control actions are both assumed to be basic closed semi-algebraic sets. So sadly, I don't have time to go into the theoretical details of all of this, but what I believe is worth mentioning is that these types of stochastic optimal control problems are, under technical assumptions, equivalent, and in practice, anecdotally speaking, often very well approximated by a primal dual pair of linear or infinite dimensional linear programs. And today I want to really focus on this sort of dynamic programming route here on the right. So don't worry too much about the notational details here. All that the problem on the left is saying is that we are looking for a smooth function w, which underestimates the value function of the cost to go associated with the original optimal control problem. And in particular, we are looking for that smooth function which underapproximates this value function as best as possible at the initial time. And from there, it will be easy to convince yourselves that we are in fact constructing a hard lower bound on the optimal value of the stochastic optimal control problem. But of course, this is still a super hard problem to solve, so we can utilize sort of the magic of the moment SumOfSquares hierarchy to construct tractable restrictions, usually in the form of semi-definite programs, simply by optimizing over some fixed degree polynomial as opposed to any smooth function. And then we can trade off more computation for better bounds and better approximation simply by increasing the degree of that polynomial. A nice thing about this approach is that it provides us with an approximate value function that then down the line can inform controller design. But, and I think anyone who's ever used these kinds of things in practice will agree with me, it's actually quite limited. In particular, the scaling isn't great, and more importantly, numerical issues are often prohibitive. So in practice, we can often only do this for moderate degree polynomials, which may not be good enough to give us informative bounds. So one way to kind of sidestep that issue, which in my opinion is criminally neglected in the literature, is that we can actually weaken our restrictions not only by increasing the degree of the polynomials that we optimize over, but instead look for a piecewise polynomial underestimator. So in particular, we can partition the state space as shown with these tiles here, as well as the control horizon of the problem, to then get a partition of the whole problem domain, which is the product of the control horizon and the state space. and then write out a problem which looks very similar, but instead of looking for a polynomial, we are now looking for a piecewise polynomial where each piece is defined on such a subdomain of this partition. And then the output is, of course, some piecewise polynomial underestimator of the value function. So then we can improve the approximation quality of this problem here, not only by increasing the degree of the polynomial pieces, but also by simply refining the partition. And while this does not offer any inherently better scaling in principle, it turns out to be quite advantageous in practice in many cases. So where does MarkovBounds.jl now fit into all of this? So the nice thing is that the Julia ecosystem in principle already supports everything that you need in order to set up and solve these types of problems. On the one hand side, we have very powerful symbolic modeling tools that allow us to specify our model data quite conveniently. And on the other hand, we have SumOfSquares.jl, which allows us to very easily set up SumOfSquares programs and then push it through the MathOpt interface to our favorite optimizers. However, if you are a practitioner or someone not familiar with SumOfSquares programming, it may not be obvious how to translate this high-level problem data to the correct SumOfSquares programs to be solved. And in fact, even if you are very familiar with these things, it may actually involve a very large amount of bookkeeping, which is error-prone, in particular if you go down the route of optimizing over piecewise polynomials. So, and that is a gap that MarkovBounds.jl attempts to fill. The idea is to only take in high-level input data and then automate the process of setting up the correct SumOfSquares programs and push it through the existing pipeline. So to show you how that may look like, I brought a small example from population control, where we are looking at a noisy environment in which a predator and a prey species interact with each other. And as long as left uncontrolled, their population sizes would show this oscillatory behavior here. And now our goal is to regulate the effort of hunting the predator species in a way to drive the population sizes to some stable desired reference value. So this whole problem can be modeled as a diffusion process, a nonlinear diffusion process to be controlled. And on the right, you see that using MarkovBounds.jl, it only takes a few lines of what I would call pretty intuitive syntax to set up and solve the associated lower bounding problems. So, and to show you that this actually works, is what I did is I ran this code and then I constructed a heuristic controller that effectively descends greedily on the approximate value functions that these bounding problems furnish. And certainly that controller, I would say, passes the eyeball test. It drives the population sizes pretty quickly to the desired reference values and holds them there. And what's particularly interesting about this approach is that because we have this lower bounding information available as well, we can actually certify that this controller is no more than 2.5% suboptimal. So what's also interesting about this problem is that it showcases quite nicely that this partitioning idea that I talked about earlier can actually be hugely beneficial from a computational standpoint. In particular, this figure here shows the relative optimality gap comparing the performance of the best known controller to the lower bound obtained by these bounding problems versus the time it took to solve these problems. So the big red markers here show the traditional approach where we are looking for a global polynomial underestimator to the value function and where we improve our approximation quality and bound simply by increasing the degree of that polynomial. So the small markers instead show what happens when we optimize over a piecewise polynomial of some given partition of the problem domain and for a degree of the polynomial pieces as color-coded. And what this shows is that when we partition the problem domain suitably, we can actually compute better bounds than with the traditional approach, and we can do it orders of magnitude faster at the same time. So to conclude, I would like to briefly talk about when you should consider using MarkovBounds.jl. So in particular, there are two conditions that are essentially non-negotiable. The first one is that you're working with a continuous time jump diffusion process, which is described well by polynomials, as discussed in the beginning of this talk. And the second one is that your state space dimension is small to moderate. So this whole thing does not scale to high dimensional processes. But once these two boxes are checked, I think there's a good case to make for using MarkovBounds.jl and the underlying techniques in one of two settings. So the first one is when you're faced with an intricate control problem, for example, because your dynamics or constraints are nonlinear, or you have other complicating factors such as infinite horizon problems or chance constraints, which are both accommodated by the package. And the second setting is something I didn't talk about in this presentation so far, but I want to mention it anyway. In particular, the techniques I talked about in this presentation extend to bounding and approximating the statistics of these jump diffusion processes as well. So this is particularly handy if you're after statistics that are rather inaccessible via sampling. For example, statistics of stationary measures, exit measures, or rare event probabilities in general. So in the future, I would like to add some support for discrete time problems and further look into the use of distributed optimization to exploit the weakly coupled block structure of these partition problems to further increase the scalability of this approach. So with that, I would like to thank all the organizers for making JuliaCon on JumpDev possible. If you're interested in the package, please check out the repository. And if you have any questions, please feel free to reach out to me.